Welcome to this second webinar on 6G Sustainable Radio Design. This is a webinar jointly organized by three ongoing SNS projects, 6G SHINE, TerraMeta, and SuperIoT. And as I said, this is the second webinar. We are planning to have a couple of more webinars later this spring. Yes, today we have the agenda as follows. We have three presenters, and then we have reserved at the end 20 minutes for questions and open discussion. And at the end of each presentation, there will be time for maybe one or two questions if there is any. And then at the end, there will be, like I say, some longer time for more discussions. So we have three presentations, one dealing with multi-criteria optimizations in hybrid optical and radio networks. The second, more on memory store-based non-volatile switches and solution process diodes. And finally, the third, more on whether using relays or RIS in conjunction with IoT. And so after this brief introduction, we go just to the presentation. I would like to introduce Mr. Mohammad Khalili from University of Oulu, and he's representing the Super IoT project, and the title of his presentation will be Multi-Criteria Optimization in the Network Layer of Optical Wireless and RF Heterogeneous Networks. Mohammad, you may share your presentation now.
Hello. Thank you for your introduction. Can you see my slides or my desktop?
Yes. Yes.
That's fine. Okay. Hello, I'm Mohammad Khalili from the University of Oulu. I'm a doctoral researcher at this university and working in Super IoT project. I'm going to present this presentation about titled Multi-Criteria Optimization in Network Layer of Optical Wireless and RF Heterogeneous Networks. Here, first I introduce optical wireless communication and radio frequency networks, and the combination of these networks in hybrid optical radio networks, and then I introduce some key challenges that may happen in research in this topic, and then I'll present some completed or published research we have done in this Super IoT project, and then I'll present our practical implementation, and finally I present ongoing research that we are doing now. First, let me introduce these networks. Optical wireless communication is a network that two well-known technologies named visible light communication and Li-Fi is our subcategory of this optical wireless communication. And another technology that have been used many in wireless communication is radio frequency. Each one of these technologies have their own advantages and disadvantages. For example, optical wireless communication provides wider bandwidth, and its spectrum is available, and there is no license. We don't need any license to use these spectrums. It provides inherent security and privacy as it only um, transmit data in confined area, and interference is reduced. But optical wireless communication has its disadvantage about mobility, transmission range. It's very short transmission range, and coverage of in optical wireless communication is very short. When we compare these two technologies, we see that if we combine or uh, integrate these two technologies, we can reach good results, might be. In practice, integration of these two technologies provide a reconfigurable network or a hybrid network that is resilient, flexible, and adaptable, and we can have the advantage of both technology, essence of both technologies, and this advantage of each technology can be covered by another one. But there are some challenges in this. First of all, let me take a closer look in these networks. In nodes that using OWC RF heterogeneous network, we have 5 modes of communication. Uh, Hybrid mode, that means a node can communicate in uplink for RF and use RF, and in downlink use OWC or optical, or vice versa. I Another way is single mode communication, that node only use RF or OWC, or another technology or another option is multi-connectivity, that nodes can use both RF OWC concurrently. Also, in access point, we have different categories of access points. Some traditional access points that are only RF. Also, we can have OWC single mode access point that only provide communication with access point using optical spectrum. But some of these access point are used only for downlink, and some of them is dual capability. Also, we can have a hybrid access point that provide two technologies at the same time. Okay, these networks in these hybrid optical radio networks, these nodes should be connected to this access point. And we can see that there are different heterogeneity in this communication. Actually, OWC and RF fundamentally have different characteristics, requirement, and objectives. For example, data rate capacity of optical wireless communication is much higher than some technologies in RF, but coverage of them is relatively low when compared by RF. Also, this heterogeneous comes to the connections. For in more detail, distinction between uplink and downlink in OWC introduces additional complexity in providing the solution for these networks. Let me uh, take a more closer look or with the more details in network layer problems in this hybrid network. One of key function in network is access point assignment or user association, that uh, a node or nodes should be connected to the access points. Here we have some devices that should decide which one of access points are more proper that to communicate or associate with it. Here we have different access points in usual RF networks, but here in hybrid optical radio networks, in addition to different number of access points that are available, different categories of access point also available, and devices or nodes should be decided which one is more proper for them. Also, we should consider that the coverage of this uh, access point are overlapped. We have high overlap between access point, and also we should consider that in some practical implementation, we need dual connectivity and multiple connectivity. That means a node can communicate or can connect, associate with multiple access points at the same time, because, for example, for reliability, to get more data rate capacity, or other advantage. Also, we need to balance the load between access points, and we know that different access points have different capabilities, different uh, requirements, and we need to balance the load between these access points, and it's very challenges. Another network layer function that uh, we need to provide some solutions for this is resource allocation. For example, in resource allocation, optimizing energy consumption. But we know that transmission power, that is the main element in energy consumption in wireless network, is totally different in OWC and RF. For instance, transmission power in visible light communication is 20 watts, but it is very low in RF. I should mention that this transmission power is for boost uh, purposes, for two purposes. One for transmission, and another is illumination. And actually, this transmission power is mainly used for illumination, and actually transmission data in VLC has very low or negligible uh, burden to the network or to the energy consumption. But the scale, we can see that scale is totally different. Or another network layer is handover management, that when a node changes its demands or move, it should communicate with different access points that are available in the area, in that environment. Traditional wireless networks so usually uses SINR or SNR. If we consider interference, it is SINR, or if we neglect interference, it is SNR. However, in traditional approach, so when the SINR of one access points come below a threshold, the node decide which one of the access point is better, and associate with the next access point. But here in optical hybrid optical radio networks, we should consider multiple metrics and SINR properties of different access points are, optical access point and radio access points, and hybrid optical radio access points is totally different, and node should decide which one access points should be connected. Also, if the nodes have the capability of multi-connectivity, the problem is more complex. Okay, we should address these challenges in hybrid optical radio networks, but in addressing these challenges, we should consider diverse requirements, characteristics, and objectives. Optical wireless communication radio frequency heterogeneous networks involve complex interaction between variables and parameters. For example, decreasing the transmission power of optical network, optical transmitter, uh, effect on the transmission power in radio frequency, but the scale is totally different. Also, we have multiple or various objectives in that in these objectives have different scales, priority, and different effect on QoS or quality of service. So we need adaptive integrated optimization strategies that should be applied for these problems. We decided to use multi-criteria optimization to balance trade-off between different objectives and have a performance that consider different criteria simultaneously. In this problem, we published some research. We have done different efforts, and we published some papers. Here I present two conference papers and one journal that is under review. In our first effort, we provided a multi-attribute decision-making approach for the problem of the access point assignment. Multi-attribute decision-making is a kind of multi-criteria optimization. In this approach, we integrate quantitative and qualitative attributes, and we use fuzzy topsies in decision making for the problem that we handle uncertainty and imprecision data that is happen in the network for the problem of access point assignment. We simulate our results. We evaluate our approach via simulations and provide a data set for this problem of access point assignment that we can use this data set in machine learning or AI approaches. In our next application, we use decentralized MADM approach, multi-attribute decision-making approach for the handover problem. I should mention that our first approach is centralized, and this one is decentralized. That means each node or each device decide locally without considering other nodes. And in here we use the Waker, another multi-attribute decision-making algorithm, and actually each node predict its next m time step locations, and for these locations it consider that if in this location I hand over the handover cost, data rate, demand to achievable data rate, and ratio of utilized to available capacity of access point for these predicted positions, and considering these three times m attributes, node use this Waker algorithm to decide to hand over to another access points or stay connected with its current access point. Also, we validated our this approach via simulation, and our result shows that this algorithm has reasonable execution time, and the performance, our performance metrics improved in terms of handover cost or data rate, balancing data rate, and it provide good results. I'm going to present this paper in very soon in Milan, Italy, in WCNC 2025. Also, we have another papers that is under review. In this paper, we uh, checked the effect of discretization that usually used in many papers. Papers we usually have decision variables, and we use time discretization and say that this variable is fixed in during each time variable during this time to next time step, and it provides a discretization. Also, a special discretization that we usually use in many reinforcement learning approach, something like this figure. Uh, and we check the effect of this discretization in OWC and RF networks, and we provided that um, s- um, s- our results show that in optical networks we need 40% more more uh, discretization in to have the same results, same SNR as radio frequency. Okay, also we implemented these networks in the University of Olo. Actually, we have a network here that this is a figure of our implementation. Here we used Beagle Bomb Blacks and a new lamp that produced in this Super IT project that is combination of VLC, narrowband VLC, and BLE Bluetooth Low Energy. And we in Super IT project we produced a new nodes. We called it Super IT nodes, and these nodes has the capability of the transmission, reception in boost technology. I means visible light communication and Bluetooth Low Energy. And but in the future we are planning to use printed electronic instead of solid networks of solid implementation. Okay, that's our network, and in this network, we collect the information from the environment and send to the cloud server, and the whole network is working well, I can say. This is some other figures. You can see that this lamp that illuminated on the one of the nodes, it communicate via visible light communication and also Bluetooth low energy to communicate with each other, and this some information collected from the nodes sent to the Scalo server. Um, I can um, talk about these nodes and this technology more longer, but due to the time restriction, let me go ahead. And currently, we are working on using AI as we the complexity and dynamicity of the network should be addressed. We are going to use RL or reinforcement learning approach to adapt to changing conditions, requirements, demands of the nodes and the network, and learn the optimal strategy over time. But we consider that we need to balance trade-off between different things. I mean that we have multiple objectives that should be improved or should be optimized. So we are going to use multi-criteria reinforcement learning for this purpose. Thank you for your attention. Sorry, I think it's a little bit longer than it's required. Yeah. If there is any question.
Thank you, Mohammed, for your presentation. I think that it was very interesting. And there is time for one or two questions from the audience, if there is any.
Yes, maybe a question from my side. Thanks, Mohammed, for the very nice presentation. I was a bit wondering what type of scenarios and use cases do you foresee for where this, let's say, combination of RF with optical to be particularly promising, or if there is a specific scenario use case you are considering in the project, or
Yes, we actually have different. As I know, we have different. We have planned to have different demonstrations and different kind of actual utilization of this kind of networks in hospitals, in tracking the devices inside factories. For instance, in hospital, you know that in hospital we are looking for accurate positioning. Another part of our project is positioning. You know that VLC is good in positioning, and so for in one of our applications that we have a demonstration on this very soon. We track the location of devices and patients in the hospital, where are them, and when they are moving from one location to another locations, and it's one of our applications that we are going to actually implement it in one of our demonstrations.
Mm-hmm. Okay, I see.
Maybe I would like to add, like as we have in the case of Mohammed, like the hospital, as we have some mobility and we are facing different scenarios with different configuration of the access point and optical and radio. So we need to optimize those and at least make decision of where to be connected to in a new environment, or even within the same environment as optical access point and radio access point from the point of view of the moving user or IoT node. So the geometry is changing with time, so we need to do this.
I see.
Yeah.
Okay, thank you.
Thank you.
Thank you.
Maybe just for there is time for just a quick question. If there is any other question, we can continue later. If not, we move to the next presentation, which is entitled Nanotechnological Advancement in Memory Store-Based Non-Volatile Switches and Solution Processed Diodes, Contributions to the TerraMeta and Super IoT. It will be presented by Jonas Dewermeyer from Universidade Nova de Lisboa.
Thank you. I hope you all can hear me and see my screen. So I'm glad for this opportunity to present here on nanotechnological advancements in memristors and solution processed diodes. And this is basically work conducted in TerraMeta and Super IoT. We are here a fabricating institution, mainly focusing on micro and nanotechnological solutions to the problems of these projects, posed in these projects. So let me begin by saying that this is, of course, a team effort, and I try to group here the people that were involved mainly in the terameter work and the ones that were involved in this part of the Super IoT work. There are more people, but concerning what I'm presenting, these are the people involved in this work. And there's also an overlap area, obviously, where we have synergetic effects from both activities. We are located here in Portugal, just south of Lisbon. Sanimat I3N is is a place where we're working, and you can obviously see we are on the far west side of Europe, southwest. So I may not have to introduce this too much, but just briefly about the Terrameter project. So it's wireless communication towards 6G. And what happens there is that in order to decrease the energy used for creating the signal, the beam needs to be directed. And then on demand and based on the scenario, the beam has to be directed to different places. And this is done by these reconfigurable intelligent surfaces, which is an array of unit cells that have a certain reflection or transmission pattern. And then once these surfaces are switchable, so basically the paths, the conductive paths in the unit cells, they can be changed by changing the state of a switch inside each unit cell. Then we can change the direction of the beam, as you can see here, mainly based on in terms of its angle. And this is what this may look like. This here is a passive example, so there's no switch in here, but as you can see, there's a place for the switch reserved. And it's normally made on a standard PCB platform by etching away the copper layer that is on it, so standard and low-cost fabrication. And this is needed because behind this surface, in a reflective case, for example, there's all the support circuitry located. And with a PCB that is easy to implement, and you can benefit from all the available technology. Problem of the PCB for us in the nanotechnology field is that it is really rough. So it's not a substrate that is easy to work with if you intend to place a switch directly in this position, directly on top of the PCB. So we measured roughnesses, RMS roughnesses in the range of 200 nanometers, and we're working with devices typically thinner than 100 nanometers. The whole device stack may be thinner than 100 nanometers in some cases. So a big incompatibility. That's also the reason why many switches which are currently used, like diodes or CMOS-based things or gallium nitride, normally have to be transferred onto the PCB. So you may do that in an optimized way, obviously, not one by one, but it's still an effort to first package these diodes or switches, and then make an array of a machine that is transferring it there and it ensures a good connection. This is all possible, but it's obviously an effort. So it would be great to just be depositing on top of this substrate, and we're working on that. I cannot present much from the solution, but that is one of the challenges that we're working on. I would like to talk a bit more about the switches that are used and the ones we are working on, where we have also made some progress. These are more traditional, or let's say more conventional switches that are used. So we have silicon on insulator, bipolar CMOS, and gallium on silicon. Those are all very promising, but they have one drawback. They need power supply in a static state. So when the switch is not changing from one state to the other, it consumes power, and that's a big problem. Here, things like microfluidics, which I'm not going much into detail, but memristors and phase change materials, which is actually one form of memristors, have an alternative. They are non-volatile, which means we change the state from conductive to insulating and vice versa, and it stays there without needing any power. And especially in applications where the switching is not constantly needed, this is a great advantage. Another thing which I'm going to explain a bit further is miniaturization. Memristors in particular, and the ones we're working on, can be made very small, and this is a big advantage for boosting the operation frequency. because as it gets smaller, we're basically decreasing the off capacitance, and the on resistance can still be high because of the mechanism of switching, which I'm going to show in a bit. And here the separation is also drawn between technologies that are then transferred typically to PCBs and technologies that are grown directly on fused silica, which is another high-frequency substrate that is often used. Here is an example for the phase change materials from a work of partners of the TerraMeta team, although it was already done before starting of the project. But you can see it's a big effort to build these devices, integrated reconfigurable intelligent surfaces on quartz substrates, since you have to make these vias, and yeah, it's of course working, but it's costly. I'd like to also, besides the roughness issue, also talk about scale differences. So if you're using a PCB, typically it comes with 35 micrometer of copper. Some come with 18 micrometers of copper, but the devices we're working with are really tiny. So they're more as I said, below 100 nanometers. And in these devices that we are also building in TerraMeta, but this is a work from literature, a two-dimensional material is used as the switching layer. So we're talking here about really a few nanometers of active material. And this then, to integrate this into a micrometer-sized structure is challenging. So I'd like to just talk a bit about the memristors, because I'm not entirely sure how known this is. So memristors, as I said, are non-volatile switches, and which can operate at high frequencies. And there are mainly two types of switchings which we distinguish. There's an abrupt switching where the high resistance state switches to the low resistance state. We can term this also the off state and the on state in an abrupt fashion. And the same applies to the reset process back to the off state. This is the switches that are most interesting for this application. Then there are also analog switches, which have a much more gradual transition and can actually also attain multiple states. Multiple states is interesting for multi-bit operation, but normally, or it is usually difficult to obtain multi-states and a high window, so a high difference between the off and the on state, which is actually the stronger requirement for the RF switch application. Then these memristors typically are separated into two categories. One is called the valence change mechanism. One is called electrochemical metallization. What is common to both of these is that there's a filament, a conductive filament, that grows through an otherwise insulating material and creates basically a short circuit. The thing is that the short circuit is reversible, and the dominating mechanism of rupturing this filament again is Joule heating. There are others, but Joule heating plays a big role in both of these mechanisms. Nonetheless, the composition of the filament can be different. It may either be made up of oxygen vacancies, or that is the most common defect, or any kind of dopant that transforms this typically metal oxide from an insulator to a conductor. But it may also be constituted of metal itself. So the metal can be dissolved at this electrode, migrate through the insulator, and redeposit on the other electrode, forming a filament, which then connects and disconnects at a small junction. And this Joule heating, what it does, it ruptures the filament just by increasing the local temperature, and this increases diffusion and makes these metallic atoms essentially rediffuse into the matrix. So when we think of capacity and resistance, the capacity can be drastically reduced by nano-sized patterning of the electrode. But since the on resistance is purely dependent on the filament size, you are basically not losing on resistance by making the device really small. So even if the active electrode is really small, really narrow, let's say, it's always going to be, so the on resistance is always going to be the same because it is determined by the filament size itself, which is not dependent on the electrode area. So you can improve capacitance by making a small device without deteriorating your on resistance. This is different in phase change materials because the whole material is changing essentially, or at least a large part of the material. This is done by applying currents as well, but the currents, they induce temperatures which are in two different regimes. So the material crystallizes and melts, or at least has phase transitions, which then give rise to different resistances. And this is somewhat more controllable than this process, but you cannot optimize it towards lowest capacitance and highest on resistance at the same time, as much as you can do with the ECM mechanism. So, of course, I think most people are aware of this, but the figure of merit for these RF switches is basically a low on resistance as much as we can, below 10 ohms ideally, and low off capacitance also below 10 femtofarad if possible. And this is once more a comparison of the different memristor technologies. So the low off capacitance is possible with both the filamentary memristor technologies. However, the valence change mechanism suffers from reaching a low on resistance. The metallic filament typically has a lower on resistance, so this is the preferred mechanism for this technology. What both have in common is cycle-to-cycle and device-to-device variations, which need to be controlled, mainly by the fabrication, but also by the operation scheme. And phase change material has other advantages, easier control circuit because you can operate it in a unipolar fashion, so you just need one polarity for operation. But it's a bit more complex. The device itself is more complex due to the integrated heater, and you can't really optimize off capacitance and on resistance simultaneously by miniaturizing the device as you are able to do with the ECM mechanism. Probably this is also this is also known for most of the people from the audience. I just wanted to show the S parameter characterization to measure these values of on resistance and off capacitance mainly, where we have like this test fixture, and we're just seeing what losses appear in both states. So once the transmission line is basically open and once it's closed, what are the reflection losses, or how much signal can we get transmitted at different frequencies with the VNA? And this is also what we subjected our devices to. So concerning the devices made in the Terrameta project, since this is work that is not published yet, but in preparation, so it's not going to be long. I'm not sharing everything, but one aspect that we do differently is the way we deposit the MOS2. We use a non-vacuum process that is also reported in literature, and it utilizes a liquid-liquid interface assembly technique, where you're basically having two liquids with different surface energies, so they form two phases, just like oil and water together, which may be a good analogy. Here it's hexane and water, and then the 2D nanosheets are injected, and they form a tiled interlayer at this interface between the two liquids, and then you can lift them out with substrate just by pulling it out of this liquid. And the sheets are, in terms of their properties, they're really good. So they are relatively large, beyond the micrometer size, and the thickness also scales nicely with the number of layers. So these then we placed between two electrodes and put the waveguide structure on top, RF probes, and tested it with the VNA. And with the embedding procedures, we could then show that in the frequency range from 10 to 110 gigahertz, we have a on resistance below 10 ohms and off capacitance below 10 femtofarads. So we're within the specifications. The details are going to be all shared in the upcoming publication. Now I'm switching to Super IoT. Luckily, there was already a nice introduction by Mohammed. So I'm going to focus on benefits of printed electronics for this technology. The main benefit is the drastically reduced material usage. You have to consider that the targets that are used, for example, in sputter deposition are made by Sol-Gel process, which is the same process that solution processing is using, just that solution processing is doing it like on the spot, let's say, so in the place where the device is built. And that saves a lot of energy because we don't need to use such a high temperature as when firing these targets. And another point is sputtering means we are coating not only the sample surface, but also the chamber walls. Plus, there are processes like etching and liftoff involved, which throw away basically largest part of the material. While here, when you think of inkjet printing, you are just depositing where you actually want the material to be. So I don't have a number here, but it is a huge amount of material that is not consumed with these printed electronics. Energy consumption I mentioned already because of the temperature, but also you don't need the RF sputtering, for example, which also consumes energy. And you can use things like road-to-road processing, which is from Emmanuel Carr's publication here, to make it high throughput. And Super IoT has this objective to build an ecosystem of IoT devices, both in terms of energy supply, networking or communication, and sensing. And in order to make this sustainable, we need such technologies that save material, save energy, and are low cost. And for these circuits that are developed here, one essential building block is a diode, and we came across a nice diode structure that can be applied to these circuits, which is compatible to road-to-road processing and works with flexible substrates. So we were working on memristors, so that's where I'm kind of coming from, and we have these zinc tin oxide memristors between two metal electrodes, platinum and titanium, and they were working pretty well. And then one typically experiments with other electrodes. Then we tried another electrode. Again, I'm not disclosing which material it is, but just by changing this electrode, we got fantastic diodes and were pretty surprised, but then characterized them further and could see that using this spin-coated zinc tin oxide with a maximum temperature of 250, we got a barrier height of 0.9, rectification of 8 orders of magnitude at 0.5 voltage, and minimal hysteresis. So currently, and then we moved further to place these diodes into a waveguide structure for high frequency characterization. This is still ongoing, but we are already seeing that we can reach about 100 megahertz. So that works for RFID applications and these things. Okay. Before I quit, I think I'm already over time. I'd just like to make a quick advertisement. So we're going to have 5 PhD positions open in the Marie Curie network with several European partners, and they're opening very soon. This or next month, they're going to open. So if you're looking for a PhD with us or with partners in Europe, please have a look at our website on EURAccess. And this is our team, and I thank you, of course, for your attention, and I'm looking forward to receiving questions.
Thank you, Jonas, for your enlightening presentation. And yes, if there are some questions, please.
Maybe a quick question from my side. Jonas, thanks for the nice presentation. So I was wondering, in practice, how fast can we switch, let's say, can we perform this switching in RIS according to all these different technologies you were presenting here?
So you mean
the order of microseconds or nanoseconds or?
Well, in fact, in these filamentary devices, in these filamentary devices, the transition can be really fast, picoseconds even.
Okay.
So they're not only consuming very little energy, but related to this, obviously, is also the switching time. So you need to apply the voltage for a very short duration. And people have shown that it's even hard to measure how fast it switches. I think the bigger challenge is probably the reliability, so the cycle-to-cycle variations. You need to find an operation scheme that doesn't destroy the device while you're operating it. So that's a bigger challenge, I'd say.
Okay, I see. Okay, thanks.
I wanted also to ask you regarding, so the memory stores, you presented like there are two sort of response, like abrupt and more, you call it analog.
Analog, yeah.
Yeah. So for the RIS, I think that we are talking about the abrupt.
Correct.
And the other one, is it so because you usually see that memory stores are thought just to be used to to mimic some sort of neurons, and
Correct.
is it the more analog sort of response for that case?
Yeah, it's mainly mimicking the synapses actually.
The
So
synapses, yeah,
the weight change in the brain basically of the synapses, and this is where the analog memory stores are mainly used for. And yeah, they work slightly differently. So we have, for example, devices that are also analog, but they switch on the whole area at the interface actually. So mechanisms then change, but yeah, both are termed memory stores and have different fields of application, certainly.
Okay, yeah, okay. Thank you. I think that
Thank you.
I will like now that we move to the third presentation, which is entitled Power Efficient Cooperative Communications with IoT Subnetworks, Relay or RIS. And it will be presented by Hamid Reza Ashenpur from Aalborg University. He represents 6G SHINE project.
Thank you. Hi, everyone. My name is Hamid Reza Hashenpur. I'm from the Department of Electronic System, Aalborg University, Denmark. I'm going to discuss about the presentation with the title of Power Efficient Cooperative Communication within IoT Subnetworks, Relay or RIS. First of all, let me introduce our project. This task is a part of the 6G SHINE project. This project aims to pioneer the main technology components for wireless in-X subnetworks for short-range and low-power radio cells to be installed in entities like robots, vehicles, production modules, or classrooms. It has a wide range of applications that has specific and extreme requirements like low latency, ultra reliable, and high data rates. You can see in this figure that we have different use cases, but I would like to say that we are mainly focused on industrial subnetwork as a special use case that we want to discuss in this presentation today. What's the goal of this presentation? Our goal is to explore power-efficient transmission protocols for industrial subnetworks. We focus on two methods of amplify and forward and decode and forward to enhance diversity, to ensure reliable and low latency transmissions. That is crucial for IoT. We then present algorithms that minimize power transmission, that not only minimize the energy, but also reduce the interference with adjacent subnetworks. That is very important in small and dense subnetworks that work in industry. To have a benchmark, we consider another scenario that secondary access points are replaced with multiple distributed RIS, and we try to minimize the efficient power transmission that is critical for our project. To have a better understanding of our presentation goals, you can see this flow chart that I show that we have we have an objective function that is about power efficiency industrial subnetwork. We consider two different scenarios. The first scenario is based on multiple APs. Scenario that one AP works as a primary access point with edge capability, and other APs work as secondary access point with just radio capabilities work and relays. We consider two different kind of relays, DF and AF relays, and the two multiplexing methods, TDMA and FDMA. On the other hand, we consider another scenario based on multiple distributed races that are replaced for cooperative communication. Before transmission, we need to estimate the channels. The channel estimation method that we use in this work is based on the linear minimum mean square approach. And after sending pilots and estimating the channels, the second task is to allocate the resources to the devices so that we can have efficient power efficient transmissions. The resources include time, bandwidth, and powers. So let's get started with the first scenario. In the first scenario, we have as I discussed before, we have one primary access point and multiple secondary access points that work as relays, and a couple of devices that are distributed among the subnetwork. Our strategy is to select one out of k available secondary access points for transmission in two hop mode, and in one hop mode we just use direct transmission to the primary access point. Then we formulate a problem for power minimization by constraint on the power and the predefined delay requirement that is selected 100 microsecond in this work. In this slide, you can see the different protocols that we used for our transmission. We consider two protocols. First is TDMA, that as you know, we use orthogonal time resources for transmission. For example, for this example, we have two different kind of devices that are scheduled to transmit in one hop, and devices that work in two hop cooperative communication. The first phase of two hop transmission occurs in the first time slots. Then we have one hop transmissions, and after that, the second phase of two hop transmission happens. So in this case, we use the whole bandwidth for transmission. On the other hand, in the FDMA case, we introduce parameter beta that is responsible for allocating the sub-channels to the devices in first and second phase of transmission. As you know, we should have some constraints on beta because the total bandwidth should not exceed the W, that is the total bandwidth of our problem. To show the overview of our communication process, I would like to show you this flow chart. You can see that first of all, we estimate the channels, then we manage the resource, and then the uplink transmission and relaying happens. By channel estimation, we mean that we use the access point, use some pilots to estimate the channels, then schedule the device for single hop and two hop. Then the resource management occurs by the primary access point for uplink transmission of devices. After that, the first phase of transmissions occurs, and at the end, the second phase of transmission in the second time slot for relaying occurs. Okay, the channel estimation is based on L training symbols that we use these pilot trainings for estimating the channels. we should emphasize that the uplink time should be subtracted by the time needed for estimating the channels for a special case that we have N devices with L pilots and with the sampling time of TS, we have this time for uplink transmission. Moreover, we should consider the outage errors for our results. We define a discount factor denoted by theta that is between 0 and 1. This discount rate is used to reduce the rate so that we have an acceptable outage at the end. One aspect of our algorithm, or the first one, is the an algorithm for relay selection. For simplicity, I just described it here and I skipped the detail of mathematics. So for each device, we compare all available links to the primary access points. I mean the direct link and all available secondary access point links, and select the links with the strongest channel gain. Then at the end, the output of algorithm is the index of 1 hop, 2 hop, and associated relays. So after in determining the relays and the devices for each category, we can minimize the power. The objective function, as we discussed before, is about the total transmitted power. Then we have a constraint on the total delay and the constraint for power, maximum power available. We consider imperfect CSI in this scenario, but it simply can change to perfect CSI by selecting theta equals to 1 and the uplink time equals to t. As you can see, the problem is non-convex. We resort to sequential parametric convex approximation, or SPC method, that's well known for solving this kind of problems. And at each iteration, the non-convex constraints or functions replaced by convex surrogates that serve as an approximation for solving the problem. So let's move to the second scenario that is related to multiple resets in a subnetwork. In this scenario, we replaced the secondary access point by some distributed resets from res 1 to res k. And each device has two available link for transmission. First is the direct transmission to primary access point, and the second is the cascaded channel between the device res and the primary access point. To clarify more about our scenario, you can see that in this figure, we use orthogonal time slots for transmission of each device. You know that a critical problem in RES is the estimation of the channels or the cascaded channels between the RES and the users. So we use a method based on linear minimum mean square error estimation, and we divide the time slot to k orthogonal time slots for each RES to estimate the channel of each RES individually. So let's move to the simulations. Our methodology is based on Monte Carlo simulation. The main simulation parameters are as follows. We have a subnetwork area of 3 square meters, and the devices are between 10 to 20, and we have one access point, one primary access point, and k different secondary access point. The packet size are different and varies from 32 to 256 bytes. The total cycle duration is 100 microsecond, and the bandwidth is 100 megahertz. The carrier frequency is 10 gigahertz, and we use the maximum power between 10 to 30 dBm. And the shadowing standard deviation is 7 dB. We also consider uniformly distributed access points and the devices in a subnetwork. we adopt ration fading for transmission because it's highly likely to have line of sight conditions in small subnetworks. The path loss is calculated based on 3GPP channel model for indoor factory subnetworks. The first scenario or the first simulation is about the CDF of transmit power per device and secondary access point for different use cases. You can see that when we adopt the multiple APs, especially the 1 of 4 approach, the power emission can be reduced up to 7.5 dB compared to just one hop transmission. That's the capability of multi-diversity for reducing power. And in the second scenario, we want to compare the TDMA and FDMA approach for both AF and DF relaying. The takeaway points from this simulation is that when we adopt DF, we achieve greater power saving. That it's due to decoding the packets and then forwarding the message. So it's more flexible, decode and forward, and have a more capability of saving power. On the other hand, FDMA generally can reduce more power compared to TDMA. That's due to the lower bandwidths allocated to each device and the lower noise power. Another slide is related to comparison with RIS. In this curve, you can see that we compare multiple scenarios from 1 hop to 1 of 4 for relaying and different number of RISes with different number of elements. For a special case, for example, this curve, you can see that we have a gain of about 10 dB compared to single hop transmission for power saving. That is that can outperforms the 1 of 4 relaying. So in general, we can say that RISes has the better capability for transmit power saving compared to relays. But I should emphasize that in this case, we didn't calculate the consumption power, I mean the circuit powers that related to each device or each elements. So it's just about the transmit powers. So in order to go to the next simulation, I should first define 2 parameters that we use here. One is overflow. By overflow, we mean that the probability that the total transmission time exceeds the frame duration. For example, if the duration time is T, the uplink transmission should not exceed this time. Otherwise, we have overflow. For the outage is the probability of failure or error for transmission for 1 hop or 2 hop transmission. So in this case, adjusting the discount rate is very important to tuning the error rate for each case of transmission. So in these curves, you can see a comparison between a relay and RIS. For example, in the right hand, you can see the outage probability against the discount rate. Generally, you can see that the RIS scenario rather can outperform the relays apart from the number of relays or RIS. So generally, relays outperforms for outage. The reason is related to active, the active devices that used in relays. But in the RIS scenario, we used some passive elements, so we don't have any capability for amplifying the signals. So that's the benefit of using relay for having more reliable links for transmission. On the other hand, for the overflow, we have another comparison that generally we can see that, for example, for this dashed line, blue line, we can see that this is related to one relay, and this curve blue line related to one RIS. So it's a remarkable gap between the relay and RIS in the terms of overflow. So generally, we can say that by leveraging the relay approach, we can reach to better reliability for transmission in this case. But as you saw in the previous slide, in the terms of transmit power, we can have a better transmit power in the RIS scenario. So let's conclude this presentation and future works. We have addressed the challenge of ultra low latency transmission for up to 100 microsecond delay for a special use case of industrial wireless subnetworks. We have a novel communication protocol for accommodating device operating in single hub and two hub fashions. We also address the problem of minimization for emitter power with coping with time constraint. The simulation results show that we can use, for example, 1/4 scheme for transmission and saving power up to 7 dB compared to the single hub transmission. Another scenario show that RIS has the capability of saving power, but it cannot compete with relays in the terms of reliability. Our future works are mainly related to heterogeneous requirements of cooperative frameworks and the flexible and full duplexing capabilities. Most of these slides and what we have discussed here is elaborated in our paper that is published in IEEE IoT journal. Thank you so much for your attention and consideration.
Thank you very much, Hamid Reza, for your nice presentation. Before we move to the question and open discussion, if there are some immediate questions on the presentation.
Yes, hi. Can I ask a question?
Hi,
Hello.
go ahead. Hi.
Thank you for a nice presentation. And I have a question. In your simulations, how do you model RIS element? I mean, just if you can a bit elaborate on that.
Yeah, it's a good question. In this scenario, we use a diagonal ideal passive RIS. So as you can see, we have different RIS nowadays, for example, from non-diagonal RIS or active RIS. But because our main task here was about cooperative communication, we just use RIS as a benchmark. So we didn't consider all kind of RIS scenario. But I think for a more comprehensive and more considering all kinds of RIS, it's a very good and valuable work to consider other kinds of RISs.
And do you see, I mean, also, did you model the loss or non-ideality is of these elements?
No, we use a model that we have no loss in the elements of RIS, but as you said, in the reality, we have some loss in the RIS elements. That is important for power consumption models, and
And do you think how much is the impact of those non-ideality effects both for communication and, I mean, is it really big? Does it have a big impact, or we can just
totally, since the devices here in the elements in RIS are passive, the circuit power needed for just is kind of the function is just a phase shifter. So we have not much. We expect to have a not more different curves for comparison in terms of power consumption. But if we want to compare the active risk, the problem is different because active risk has some active elements that uses more power for amplifying the signals. So in the case of passive elements, I think it's somehow feasible and relevant that we just consider the transmitted power for risk in. Yeah.
Thank you.
Thank you so much.
Any other question or comment?
Maybe just a comment to what Hamid said. Isn't it to me that also the non-idealities, even of the risk implicitly, they are captured in the channel estimation error model that you are including in your studies. So if there is some issue with the phases and so on, this is somehow can be captured in the non-ideality of the channel model you're considering, right? You are muted, Hamid.
Yes. We in the phase of channel estimation, we have the capability of compensate all the non-ideality of the channels. But this risk problem is an open problem that is not has many aspects that it should be considered for using in practical scenarios.
Yes, I also wanted to ask you, based on your result, we cannot simply say that RIS is the best or relay is the best. It depends on the sort of performance. How about if we consider the overall complexity of the system? As you know, if you have a RIS, you need to have a control system and this kind of things. And is it so that the relay approach is simpler?
Yes, the relay approach is simpler in the sense of the number of parameters that should be optimized or controlled. When we have release, we have to control the risk elements for precoding for optimizing the precoding or beamforming for each device. So it's very highly loaded for the access point, the primary access point or the main controller to design the precoders for each scenario. And by changing the CSIs, we have to rearrange all these precoders for each device. So the overall overhead of the RIS, especially in the case that we have lots of number of elements that is relevant for the case of, for example, FR2 or millimeter wave, we have in the sense of thousands of number of elements. So it's a very highly loaded problem to optimize jointly the precoders and the powers for this kind of problems. Yeah.
And then when if you have mobility and you need to do this to track the situation, so this consumes a lot of resources.
Yeah, it's a very nice comment. I forgot to say that we consider in this scenario a static case, that all the subnetworks, all the devices are static. But in the reality, we work with the mobile and highly dynamic scenarios that change overall the channel conditions. So when we are facing to a problem of risk, the dimension of the problem increase dramatically compared to relay.
Yeah. And then if you have multi-users and mobility is even worse.
It's even worse. Yeah.
Okay, thank you. And I think we have 10 or 9 minutes till the end. I would like to ask the audience if you have a question to any of the three presenters, or also if you have some suggestions for topics for the upcoming joint webinar, just please ask or suggest.
Maybe possible, I have a question for Mohammed for the presentation by Mohammed. There is an aspect that maybe I didn't really get very clearly in your presentation. So at some point you mentioned something like the power reduction in this VLC in your heterogeneous setup and so on. The power reduction in optical impacts the RF differently.
Yes.
So I'm not. Can you please elaborate a bit more on that, because probably I missed what you meant with that.
You can when a node have a data rate demand, it should receive this data demand from 2 or 1 access point, and a node that is connected to one visible light communication or optical wireless communication, it can receive high bandwidth or high data rate with very low energy consumption for transmission. But if not disconnect from this access point and connect to another RF access point, as the transmission power of the radio access point is different, has different scales, and this node to receive this data rate demand, we have higher bandwidth, and the scale of this transmission power is different for that. For instance, for this optical communication, it consumes
Much higher power. Yeah.
It's the scale, so it's totally different. And to provide this demand of data rate, or maybe this radio access point need to employ high transmission power.
Okay, so it's mainly related to this big imbalance that you have between RF and optical transmission.
Exactly.
Yeah, I see.
Exactly.
Okay, thanks.
Welcome.
Any other question or comment from the audience? Well, I think we are almost done. We have still 5 minutes, but if there are no questions, I would like to thank you all, particularly the presenters, but also the audience. And I think it was a really nice webinar covering different aspects of sustainability from our project's point of view. And once again, we plan to continue with 1 or 2 webinars this spring. So stay tuned. We will at some point inform about the date and agenda of a new webinar. With that, I want to thank you everyone for your participation. Thank you. Bye-bye.
Thank you very much.
Thank you, everyone.
Thank you.
Thank you.
Bye.
Bye.
Bye-bye.
Goodbye.